Good morning, everyone. Thank you for joining us. I'm Abhishek Kashyap. I'm the product manager for BigQuery ML, and I'm going to talk about what's new since we launched it last year. I'm also joined by my colleague, Robert Saxby from Google, and most importantly, Jonathan Poelhuis, who's a senior data scientist at Booking.com, and Timo Kluck, who's a principal developer at Google.com. So while I will talk about some simple SQL, Booking is going to walk through a really interesting use case of data quality. And trust me, this is going to be the least interesting chart that they show. And we'll have a quiz later where they'll show you what this means. Some of you might have seen it, but it's really as exciting as this chart is. And after you do what they do, your data is going to look this beautiful when you think about its quality. So let's start with BigQuery ML. We announced it last year, and we have stayed quiet since, as we have been building a bunch of useful things for you. To give you a recap, what is BigQuery ML? BigQuery ML is a SQL interface for you to do machine learning where your data is, and in this case, BigQuery. You simply call create model to build a model, and predict to do predictions. What this gets you, you bring machine learning to the data. And as data and machine learning are so intertied, feature engineering is such an important part of machine learning that helps you very rapidly build machine learning models by using SQL for data engineering and SQL for building the models themselves. And furthermore, we automate a lot of things that a good data scientist does. So that saves you a lot of time as well. So we showed a couple of SQL queries, just create model and predict. Now, all of you who have tried machine learning know machine learning is not that simple. So what are the things that we do behind it to get you a good model from a simple SQL syntax? One, you don't have to worry about how big a cluster you need to provision. You just use BigQuery, and you're all set. We auto-split data into training and test, so your classification or regression models do not overfit. We standardize all numeric features, one-hot encode all strings. We impute null values in your data, both during training and prediction. Again, something that you would have manually have to do otherwise. And if your classes are imbalanced, we actually do handle that as well. And we always give you options to change what we do automatically here. We had many, many customers use BigQuery ML. We have had support for linear regression and logistic regression so far. Even with those, these are some of the public references for customers who worked with us during beta. And what we are announcing today is BigQuery ML is going to be GA. It's coming very soon. We have added evaluation charts for classification models right on the BigQuery UI. I'll go through some of these pretty soon. If you wanted to do customer segmentation on your BigQuery data, Kmeans clustering is available in a public beta today. We have added support for a few more models. These are in alpha. Now, alphas are private. They are under NDA. Please get in touch with us if you want to use them. The models in alpha are matrix factorization. So if you wanted to build recommendation systems, like the Netflix movie challenge or a recommendation system for your shopping cart, you could use matrix factorization for that. We have added support for building deep neural networks, both a classifier and a regression model, by using TensorFlow under the hood, again, all from BigQuery ML. Furthermore, if you think about your production pipelines, you can now start importing TensorFlow models into BigQuery and use them for batch prediction. And we have also added some preprocessing functions, so you can do SQL-based transformations for your feature engineering. And I'll get to it in the next few slides as well. So the first one, for those of you who have some machine learning experience, the first thing you do after building a classification model is to look at statistics like precision, recall, ROC curve, and you want to play with the threshold to see what's a good threshold to pick and to go back and improve the model. So now when you build a model in BigQuery ML, right on the BigQuery UI, you click on the evaluation tab of a model, and you see this interactive chart where you can slide the threshold and see what precision and recall you get. When you're working with a multi-class logistic regression model, you will see a confusion matrix. That's the chart you see on the right top. And while you are training the model, you can monitor the loss as a curve rather than just a table, which is the chart you see at the bottom right. Moving on to the first model we are adding support for, which is matrix factorization. This is typically used for product recommendation, offer matching, or if you had an app, you could recommend groups to people on your app. For all these things, the idea is that you have a set of user item rating tuples. You don't have data for all the users and all the items, and you want to predict the user-item interaction for observations we have not seen. Now, there was a challenge that Netflix had a few years back where they challenged people to do movie recommendations. With this simple SQL and some L2 regularization, we pretty quickly got to the same performance as what Netflix got with matrix factorization back then. This comes with all the linear regression functions that you have seen to see the root mean square error, to see other metrics, get training info, etc. And we have added a new function called ml.recommend, using which you can get the full matrix back for all user item pairs. Again, this is in alpha. Please reach out to us if you would like to try it out. The next model is deep neural networks. Again, with the same create model syntax, you just say model type equal to DNN classifier or the regressor, and we will build a TensorFlow DNN for you. A lot of times, linear models are not good enough based on the data set you have, and to capture that nonlinearity, DNNs work pretty well. We have the usual options and defaults, which we set to a good default value if you do not choose them. To give you an example of how this could work, if you know about the NCAA competition, it just finished on Monday. Google is a partner with them. So we were doing a prediction on the number of three-point attempts in these games. We trained a global model. We trained a logistic regression model using BigQuery ML and a DNN classifier. And we had a label into 5 buckets. What we found was, while the regression models work pretty well for the average case, for average teams, when you look at a top team like Auburn, which actually beat UNC with 65 attempts, those edge cases, you need to have a lot of nonlinearity to handle those. And you can see in the last bucket, the DNN model predicted with a 72% likelihood that it's going to be more than 55 attempts. The logistic regression model did come out highest at 27% among all buckets, but you couldn't be that sure if you were to use that model. And if you just look on the left, that's the query you have to build this model. Just very few parameters. We built this. Most of the work went into creating these features, which again is best done in SQL in BigQuery. Now, the next thing, which is not a new model, is what if you have data scientists building TensorFlow models outside? These could be for text, images, or just nonlinear models for structured data, but your production pipelines are through BigQuery, say using Composer or Airflow. You can now use create model to have the model picked up from GCS and deploy in BigQuery and use it for predictions using the same predict syntax. During alpha, we have a model size limit of 250 MB, and we have a restriction that your output row needs to depend on one input row, which means you cannot yet import RNNs or LSTMs. But this works for most TensorFlow models that satisfy these conditions. Last but not the least, we have added support for pre-processing functions in SQL. So we have added this transform option through which you can now define all your pre-processing during model creation. And during prediction, you do not need to remember them. As long as you select the same columns, we are going to apply the transformations automatically. So you can even start differentiating between users who can build models and users who use them, because they don't have to remember transformations anymore. And we are adding some common pre-processing functions like bucketization, creation of cross features between numeric features, which is called polynomial expand. And the list will just continue to expand with time. So you can start doing more and more with SQL right here. And before I hand it over to my friends at Booking, I actually wanted to show a demo here. Can we go back 2 slides, please? Can we switch to the demo, please? Okay. So one of our partners, GrooveNots, built this web app for us. And what they did was they built a TensorFlow model for categorizing images. So you can look at 2 images and say if they are similar. And if I just click on the middle image, what it does is it calls ml.predict on this TensorFlow model from BigQuery ML, and it compares it with a million other images and comes back with the images which are the closest. Now, the model was created outside. It's on images. It's a highly nonlinear neural network. And it's all working within BigQuery. And you can see the images are all pretty close. To show you the SQL, what it's doing is it's calling ml.predict, storing the vectors the model gives in a table. Then it's taking the image I selected, and it's getting its vector right from BigQuery through the model we have imported, and then calculating distances between all other vectors and just sorting them. So this is all SQL. There is no UDFs. You don't have to go outside. You just import the model and run it. That's how simple it is. If you can go back to the presentation, please. So what's available today in beta is Kmeans clustering. That you can, the most common use case is customer segmentation. But Booking will talk about using it for data quality as well. And I'm very excited about it. Again, you just say model type equal to Kmeans. It will create the clusters for you. You can inspect those clusters. And the most important is you can get the centroid information by calling a function called ml.centroid. And it does work with almost all BigQuery data types, including GIS. So with that, I'll hand it over to Robert and Timo. Thank you.
Thank you, Abhi. Timo and Robert, I'm with I'm with Booking.com. For those of you who don't know the company, it's for an international audience, it's maybe well known. We're in a similar space as companies like Expedia and Hotels.com, but Booking.com is quite global. It's actually the 8th largest internet company of the world with over 28 million listings. we're mostly based in Amsterdam, but also 200 smaller offices in many countries across the globe. The actual problem that we're trying to solve with BigQuery is the following. For some of the people who have used our website before, they may recognize this the screenshot of our search results page. And I've highlighted on the left side the room facilities filters. Now, what that means is that if you're looking for a place to stay, maybe you're specifically interested in having a kitchenette, having toiletries, having maybe a view. And there's many different room types that may satisfy those constraints. So for example, many hotels may have a room type for a bridal suite, for twin rooms, or maybe even the cupboard under the stairs. Now, from having these facilities right is actually quite important both for the hotel and for the customer. We don't list them all here on the filters, but there's actually 176 in total. And you can imagine from a customer perspective, if you filter and are specifically interested in having a room with a view, then if that data quality is off, and we specify that we have it, but in reality it's not there, then you may be very disappointed. Conversely, from a hotel perspective, if you actually do have a kitchenette available, but you don't list it here, then you may miss out on guests that would have otherwise stayed with you. Now, so that is just to illustrate that having this data quality very up to date is important for hotels and for guests, and therefore specifically for Booking.com as an intermediary. Now, more specifically, this is quite a large data set. We have hundreds of millions of rooms types. So this is a table with hundreds of millions of rows, 176 binary fields. Binary as in it's a Boolean. A facility is either there or it isn't. A room either has a flat screen television or it doesn't. There's daily changes to this, and that's in many cases a manual process. So that means that it's actually the hotel owner, the property owner that makes those updates in an interface. And so issues that may exist with that data, and these are some examples that we'll see in more detail, is you cannot actually have pay-per-view channels in your room if you don't have a television. Now, this is one rule, and it's obvious if you know it, but we'd like to actually find more of these rules and try to identify these kind of issues without having humans interpret them. That's based on the following premise. So the core assumption is that generally our data is quite good. So that means that it represents it represents the problem domain quite well, and also in most cases the data quality is adequate. And if that's the case, then that may mean that we should automatically be able to infer any issues that arise with that. Now, with that is where we were interested in seeing whether BigQuery ML could help us with that. And I'd like to hand over to Robert for explaining that in depth.
Hi, thanks, Timo. So just to dive a little bit deeper, quick raise of hands in the audience. Who's ever worked with clustering, Kmeans, or otherwise? Okay, so bear with me a little bit. 176 features, 176 dimensions, and they're Boolean. So that means we have 2 to the power 176. We'll come back to that in a moment. Imagine for a moment that you were trying to codify, as Timo said, that's going to get really tough really quickly. I mean, if you were to try and work out all the combinations to the power of 176, like that's how many you have to kind of think of. There's something you don't want to maintain. So we're looking at, like, can we put this data together? So can we cluster it? So let's have a look at what that would actually look like. You saw from Abby's presentation that this is K-means clustering. It's in beta, so you can give it a try yourself. Here is a diagram I'm just going to walk you through, which is basically what's happening with clustering. So you have your observation. This is 2 dimensions. Remember I said we have 176, but let's start with 2. So you have data points in 2 dimensions, and you basically want to see which data points are close to each other. So working on that assumption that our general data quality is good, and working on the premise that things that are similar are going to be grouped together, we can apply an algorithm that starts grouping those things. And this is basically what happens. as you run through the clustering algorithm, this is happening in the background, of course, it's going to actually work out which points belong together, and you end up with these nice clusters. These points, with the triangles highlighted around them, these are the outliers. These are the points furthest away from their centroid. The centroid is the black star here in the middle. So if we look at this cluster, if we look at this grouping of things, we can ask ourselves a question: are these points that are far away from the centroid? Why are they different? What makes them special? And remember that our problem space is data quality, and we're looking at these room facilities. So we have a room type. If you think about a hotel, it's got different rooms: bridal suite, normal room, standard room. And for each of those room types, we'd expect to see some facilities. Now, why are these ones further away from their clustering? So in the demo in a moment, we will see a little bit more about that. So I will be calling Jonathan to the stage. But before we get there, I just want to show you a little snippet of the data. And just to kind of give you an idea of like what's being done for you in the background. This is the data. It's a very wide table. It's very sparse. As you can see here, actually, all of these particular observations, everything is false, so it means it's not available. So it's a sparse data set. We have here just a few examples like telephone or TV. Let me go to the next one. So when we look at clustering, so particularly we have Boolean data, so it's either available or not. These need to be embedded, and we're going to be measuring distance with cosine because we have a very sparse and deep data set. So we move on. I thought this visualization is quaint. It's going to get better in a minute. So imagine a cube. We saw that clustering a moment ago with 2 dimensions. If you take a cube, now you have 3 dimensions. If you start putting cubes inside other cubes, you can have 6 dimensions. You put it inside another cube, you get another 3 dimensions on top of that. Coming back to this diagram, this is what 15 dimensions looks like. I tried to find one for 176, and my laptop stopped working. So try to imagine in your head what 176 dimensions look like. So before we go to the demo, I just want to kind of walk you through the steps that are involved in this work. So this work, first of all, is like preparing the data. So that's super simple. We're in BigQuery already. Our data's available. We can apply some SQL to actually clean things up or, select the dimensions that we're interested in. In this case, we're just grabbing all of them. You saw the statement earlier about how you train. So it's basically create model. You set the option types as Kmeans. For our distance metric, we're using cosine similarity. And then you just basically select from that table. This is unsupervised learning, so you don't need to provide a label. And once we've done that, we take that model, and then we basically predict for every row. And what that's going to do is assign every row, so every observation, to one of those centroids. And that value is basically how many clusters you have. So that's the K that you see there on the left. So we have to pick a choice for that. The number that we pick to start off is just log base 10. You saw it as the kind of default, what we suggest you should take of the number of observations. So we're in the tens of millions of observations, so we pick 7 as a starting point. And then we run the algorithm, we do the prediction. After we do that, we want to explain the clusters. So what are the clusters actually telling us? So in the demo, what you're going to see is how we use some SQL and Data Studio just to kind of visualize that so we could start interpreting what's going on. And then once we've done that, we actually want to go and explore some of those outliers. And this is where it gets interesting. So Jonathan, please. Can we switch to the demo, please?
Wonderful. Good morning. The first thing I want to show you is the SQL itself. So why did we want to play around with BigQuery ML? Well, it gives us a very quick iterative place in line to be playing with these kind of things. So the longest part here that you see is selecting all the features that we have. OK, that's a little bit cumbersome, but note that creating the model itself is super fast and easy. That's convenient for us. So you choose the model type, Kmeans. You choose the distance type. Robert explained that we're going to use cosine because of the shape and type of our data. And then the one thing we had to play around with, which was interesting, is what's the number of clusters we should choose? We're not trying to predict here. We're trying to find interesting things that will help us improve the quality of our data. So we started with 7. We tried some other multiples. Let's see what that data looks like. OK. So I'll start with if we use 7. So let's start with the default. What are we seeing here? So there's a handful of graphs on this Data Studio page. It was very convenient moving data between. So on the right-hand side in red, you see the clusters. You see their rough sizes. So some are pretty small, some are very big. Okay, and you also see something about the distance between those clusters, as in the higher you are up, the farther you are away from all the other clusters. So these are the centroids. What we're seeing here at 7 is that maybe there's a bit of a, cluster 1 is a bit farther away, but it's pretty uniform. What do we see in green here? So we thought within each cluster, how do we define outlier? It could be a cluster that's very far away from others, or it could be points within a cluster that are very far away from their centroid. They're in this group, but very far away from neighbors. So it could be both of those things or either. So if we look within each cluster, say if we look at 5 here, this is something about the distribution of distances from the centroid of points in that cluster. So if you're at 0, you are the centroid, or you're at the centroid. If you're at the max here for cluster 5, it's 0.59. That means you're 0.59 away from the centroid itself. And we have something like you have the max there, you have each of the quartiles. It gives you a flavor of where the data is. The darker the bars, of course, these are the second and third quartiles. That's where most of the data is in these cases. Okay, we've played around with 7. It turns out at 21, we started to see quite some interesting stuff. So again, look on the right-hand side. We see the distances going up. This is sort of natural. You have more things, so you're farther away from the total of them. But also, this means that the clusters themselves are getting better defined. So they're farther away from each other because they're better defined. But maybe most interesting, you see cluster number 10 here is really getting pretty far away. I think there could be interesting things there, and we'll see in a minute that that's true. And if we look again back at our distances, so we see that cluster 10, okay, so these are all the distances from the centroid to the point within that cluster. The max, the long tail to the right, which we'll see in a minute, seems to be higher than the other clusters. Again, maybe for both reasons, we should probably start looking here for oddities, things that we might be able to fix. If we drill in there, we see something like a bell curve distribution, but remember, we really care about the things far away from the centroid. So far to the right, indeed it's kind of bell curve. You could look at the long tail to the left, but that just means it's very close to the middle, very close to its centroid. That's okay, but for our purpose, we really care about, why are you so far away? All right, well, how do we define that in a way that we can then drill into? Let's look a little bit at some SQL here again. There's quite a lot here, but maybe the most important thing to see is that we're just going to define outlier for our purposes as being 3 standard deviations to the right in that bell curve. So I want to be very far away from the centroid, and then let's inspect them. Let's see if that is actually shaping up to be what we think it looks like. If we go back to our data studio here, I want to look at outliers for those 21 clusters. Okay, so first of all, the donut here is indeed the outliers coming from each of those clusters. So we're going to inspect some of these. Of course, we're going to first look at 10. We saw that cluster 10 was already kind of odd for at least 2 different reasons. I kind of hope its outliers stand up for that. Now, what do I see in this bar chart? So each one of these pair of bars, red and blue, is one of those features, one of those room facilities. The blue is the location on that axis of the centroid, which, because we have Boolean data, is actually the average availability of that feature for the points in the centroid. We're kind of lucky in that case. It's pretty interpretable. So take this first one. Toilet paper is available for 99% of the points in that cluster. Okay, refrigerator would be 99% again. So this is very common for points in this cluster. What does red mean then? For all of the outliers we've chosen, that's the average availability for that feature, for that room facility, for the outliers. Okay, this is still aggregate. Why don't we drill into one of these and see what we see? Now, maybe one more thing to note is that farther to the left, it means it's more important, more common for this thing to be available. Farther to the right means less available within this cluster. It helps us get oriented on maybe what's important here. All right, If we drill in, let's take the first one. These are ordered by distance from centroid, so I kind of hope that this first one is very odd. All right, things have gotten a little bit simpler to interpret because I have only one instance now. So you see the red bars have disappeared in some cases. That means that thing is not available for this instance. If you see a red bar, it means it is available for this feature. Okay, so if I'm paging through here, I see what's available for this outlier. Well, I see a dining table. Okay, I see a toilet, a shower, maybe some body soap. That's nice. Bath or shower is there. Free toiletries, even shampoo. Okay, this is all good stuff. Where do you put all those things? Well, you might want to put them in a bathroom, and I think it's not here. Can I find it? If I can find bathroom. Yeah, there it is. There's no bathroom. Well, this might be correct. I don't really know, but it's worth looking into it with this property, I would think. Even worse than that, you got a lot of free toiletries, but wait, there is no free toilet paper. Now, BYO toilet paper is not how I wanted to travel to San Francisco, but maybe your trip is your trip. That's okay. But I definitely want to follow up with this property because, hey, if I don't have a bathroom, if I don't have free toiletries, I very well might be missing out on filters of users looking for properties with exactly those things. Or I might be surprising them. You look on the hotel page finally, you got them to click and wow, it's not there. That makes me worried. Okay, that's interesting. We've seen one example here. If you look at the other examples in this cluster, it's actually quite similar. It has a lot to do with missing pieces of the bathroom that might be correct, might not, but they seem odd, and it would be worth looking into this to improve the data quality. Can we go back to the presentation? I've pulled out a few others that have a different flavor. Let's see. Okay. So if we look at a different one here, this is from a very different cluster, so very different important things. If you look to the left there, you see very different kinds of features that we care about. I see toilet, bathroom, free toiletries again. Okay, that's quite interesting. What's available there? So if I look at this, this is, remember, just one instance. I see an interesting, I'm going to shift away from bathroom just to mix it up. I see cable TV, or cable channels, sorry, and I see satellite channels as well. Okay, that's quite nice, but I do not see a TV or a flat screen TV. Okay, so you have all these channels, but you have nowhere to watch them. Still, it might be true. I don't know. I'm not sure how this property works, but I'd want to follow up on that. Somehow you're going to be missing out. If someone filters for flat screen TV or a TV, they're not going to be able to find you, even though you have these very nice facilities. How about one more example? So again, from a very different cluster, we want to look at what's available here. I've got some arrows there. I see refrigerator, I see stove, I see toaster oven, all kinds of really convenient stuff. I think I see microwave in there somewhere, electric kettle, even dishwasher. Where would these things go? In a kitchen, right? You assume that there must be a kitchen there, but I don't see kitchen. So again, you're going to get filtered out. You're going to be missed by all these examples of visitors trying to find you. That's a big miss, and it's also something that we as Booking.com want to get right as the intermediary. So we've seen a few examples. We've gone through the whole cycle here. Now we want to make this actionable. We'd really like to make this useful and bring some value. What would we like to do in the next steps? Well, I could imagine ways that we would like to use this. We could surface this kind of information periodically to account managers or to property relationship managers so that they can double check this information, make sure that properties aren't missing out. We could also automate it in such a way that this is surfaced on the property management page that we facilitate for the customer itself, for the property, so that they can make sure that this is correct for them because it really matters. Of course, all of this was by hand. It was very convenient. It was easy to iterate because it's all in SQL. But we'd love to pack this into something that runs pretty regularly and does all the surfacing for us. We'd also love, we played around with hyperparameters. There are ways that you can optimize this, but we're just exploring. We'd love not to explore every time if we make this actionable. And anything else? No, well, we're heavy testing culture, which means we have this idea, we think it's useful, but does it really bring value? We'd love to put this kind of information in some kind of A/B test, maybe fixing the things that we find wrong, and hopefully showing that it does indeed bring extra value. It does help customers find what they're looking for. Finally, maybe one more improvement would be that you saw 176 dimensions, very sparse. We employed some techniques, but maybe not the best ones for dimensionality reduction. Clustering in 176 dimensions is kind of tough. We'd love to see something like PCA in the transform bit in BigQuery so that we can, in a more mathematical way, make this problem a little bit lower dimensional.
Microphone back on. We promised we were going to put Abby on the spot, and we said, like, yeah, it's great we have all this. We got some nice pre-processing, so we want to see PCA up there. I mean, just give a little cheer if you want PCA as well, so Abby gets the... There you go,
right.
Abby. Just one more step on the automation. I just wanted to kind of like really bring this home, that all of this we did in BigQuery, the visualization we did in Data Studio. If we were to automate this, we could use scheduled queries, or we could use something like Composer. And just think what this means to folks that, that aren't maybe, familiar with programming, or this is a great tool for your analysts to start actually working out, or even for your data scientists that want to kind of go in and start exploring stuff. They come in there, they're in the BigQuery, the data's already available, they can start manipulating the data, run these models, and actually start surfacing these results. With a little bit of glue using something like Composer, we could get those results out, send them off, and really start making this something that helps us improve our data quality issues. So we're going to do more with this. We're going to try and follow up with a blog and hopefully build a solution around it. So keep an eye out. With that, I'm going to ask Abby to come back and maybe finish things up before we hand over to questions.
Thank you, Timo, Jonathan, and Robert. This was one of the most exciting use cases I've seen of clustering so far. So what do you do next? We actually have had a course on Coursera that you can go take. We added a few tutorials and samples to an Apache project on GitHub. That's the bit.ly link. You can go download them. There's documentation. You can start using it. We have another great session where AAA and Maven Wave at 2:10 today, where they'll show you how to use BigQML through Sheets. So your really non-technical users can start using the predictions. You can go to the Booking.com data science blog to learn about other exciting things we are doing. For all the alphas I mentioned, please reach out to us. And we are always available by email for any questions or feedback that you may have. After the session, please do rate us and send us feedback. That's very useful for us for planning. And with that, we are open for Q&A. Thank you.